All right, let's go way back. We're talking 1999. Think about it. This is before big data was a buzzword, before we all had supercomputers in our pockets, a time when researchers had to get really creative. And that's exactly what a team at MIT did. They took on a challenge that's still mind-bogglingly hard today. They tried to teach a computer how to actually watch and understand a game of American football. Seriously, let's get into it. So, picture this. You're the video coordinator for a football team. The coach storms in and says, I need every single offensive play from the last 3 years, but only the ones inside the red zone, on second or third down. Oh, and I need you to separate out the draw plays from the sweeps and the traps. I mean, can you imagine? You'd be buried in game tape for weeks. That grueling manual job is the exact problem this MIT team wanted to solve. They asked a simple but revolutionary question. What if a computer could just do all that for you? So this wasn't just some thought experiment. This was the real-world goal for a team at the MIT Media Lab. And you got to keep this in mind. We're not talking about 2024 with all the fancy AI we have now. No, they were taking on this beast of a problem back when the 20th century was just about to close out.
The technical term for what they were trying to do is video annotation, but that sounds a little dry, right? What it really means is teaching a computer to tell the story of what's happening. It's not just about object recognition, saying that's a player, that's a ball. It's about understanding the entire sequence of events, the action. It's the difference between seeing a bunch of pixelated blobs and actually recognizing, that's a P51 curl pass play.
And I just can't stress this enough. The year is 1999. Forget high-definition video. We're talking blurry, standard def, sometimes even black and white footage. There weren't any giant data sets on the internet to train their AI on. The computers they were using had less power than the smartphone you're probably holding right now. So that coach's request, it wasn't just a tough challenge. To most people, it would have sounded completely impossible.
So where do you even start with a problem like that? Well, the very first hurdle was just seeing. How on earth could a computer track a bunch of tiny, blurry shapes when the video quality is low and the camera is fly all over the place?
I mean, look at this list of challenges. The camera is constantly panning and zooming. The resolution is so low that players are literally just 10 by 10 pixel blobs. The camera lens itself is warping the picture, and that's before you even get to the players, who are moving in these chaotic, unpredictable ways, crashing into each other and blocking the camera's view. Seriously, any one of these things would be a total nightmare for a computer vision system back then, and they had to solve for all of them at once.
So it all comes down to this really fundamental question, right? How do you track players you can barely even see? You can't understand the strategy of a play if you don't even know where the players are.
And here's their first brilliant move. They realized the football field itself is a constant. It doesn't change. Its dimensions are always the same. So they used the field lines, the yard lines, the hash marks as an anchor. The system would find those lines in the wobbly video and basically stretch and warp the image until the field was perfectly flat. It's a process called field rectification, and the result is amazing. It transforms that shaky, distorted camera view into a stabilized, top-down, God's-eye view of the game. Just like that, the camera motion problem was solved.
Okay, so the view is stable now, but tracking 22 players all at once is still way too hard. So they came up with another genius hack called the closed world assumption. Think of it like this. Instead of trying to solve one giant, impossible jigsaw puzzle, they decided to cut that puzzle up into dozens of tiny, super simple puzzles. They broke the field into these little independent regions. And inside each of those tiny worlds, the computer only had to solve a much easier problem, like track that one player against the green grass, or figure out what's happening with these two players in this hash mark.
And the payoff for this was huge. By focusing on just one small area at a time, the system could get way smarter about what it was looking at. For example, if it's tracking a player inside a world that has a big team logo on the grass, it can learn to just ignore the logo. It focuses only on the pixels that belong to the player. It's a form of context-aware tracking, and it was a massive breakthrough for them.
Okay, so at this point, the system can successfully track the little pixelated blobs as they move around this nice, stable, top-down field. Pretty cool. But that's really just step one, isn't it? Knowing where the players are is one thing. The next giant leap is figuring out who each player is and what they're actually trying to do. This is where we move from just seeing to actually understanding.
And right away, they hit a classic chicken and egg problem. Think about it. How do you know who the quarterback is? Well, he's the guy standing behind the center. Okay, but how do you know who the center is? He's the guy in the middle of the offensive line with the quarterback behind him. See the problem? Every position is defined by its relationship to the other positions. It's a circular puzzle. Where do you possibly begin?
Their solution to this was just so clever and logical. They decided to forget about motion for a second and just solve it like a static logic puzzle. Here's how it worked. First, the system would get the starting XY coordinates for all the players on the field. Then it would basically make an educated guess, a hypothesis. It'd say, okay, what if this is the line of scrimmage? And then it would check that guess against a huge rule book. Hundreds of rules about how football formations are supposed to look until it found a combination that made perfect spatial sense for all 11 players on the offense.
And boom, the result was a perfectly labeled formation. This is the key part. Before the play even starts, the system now knows who's who. It's figured out the quarterback, the center, the wide receivers, all just by solving that static spatial puzzle. All right, so the system knows the starting lineup. It knows who's where, but football isn't a static game, right? It's all about what happens after the snap. And that brought the researchers to the final and by far the hardest part of the whole problem, understanding movement over time. Now, instead of trying to analyze the messy video frames again, the system did something much smarter. It focused only on the paths the players took, their trajectories. You know when you're watching a game and the announcer draws those lines on the screen to show a player's route? That's basically what the computer did for itself. It transformed all that chaotic motion into a clean, simple chalkboard diagram showing exactly who went where. So how does it make sense of all those squiggly lines? They used a pretty advanced statistical method called Bayesian belief networks. Now that sounds super complicated, I know, but just think of it like this. The system had a bunch of tiny detectives. Each detective was an expert in just one thing. So you'd have one detective whose only job was to look for a quarterback pass drop back. It would look at the QB's trajectory and say, he's moving back and to the side. That looks like evidence for a pass. The system would then listen to all these little detectives, weigh all their evidence together, and build a convincing case for what kind of action was unfolding. And what's so cool is you can literally watch the system's confidence grow over time. So right after the snap, at frame 10, the QB has only taken a few steps. The pass dropback detective might only be, say, 20% sure. But then, as a few more frames go by, he keeps dropping back, more evidence comes in, and suddenly the system's certainty jumps up to 85%. And by frame 40, it's 95% sure. It's not making a snap judgment. It's building its belief as the evidence unfolds, just like a real person would. Okay, so let's put it all together. They figured out how to track the players, they solved the puzzle of identifying their positions, and now they can recognize individual actions based on their movements. So when you stack all of those layers of understanding on top of each other, what's the end result? You get the whole shebang, the holy grail, a system that could recognize entire, complex plays straight out of the playbook. And we're not talking about just general categories like it's a run or it's a pass. No way. The system was identifying specific, named plays from the playbook, things like P51 curl or P54 max cross. It was actually reading the game tape with the same level of detail as a human analyst. That impossible request from the coach at the beginning, they had actually done it. But here's the thing that makes this accomplishment truly incredible. The data they had to work with was terrible. Even the information they entered by hand to test the system was noisy and jittery. Think about it. Where do you even click on a player who's falling down? And a tiny little mistake in marking a player's position on that wobbly video would get magnified into a huge error on the clean top-down view. So, they pulled all this off while working with messy, imperfect, fundamentally flawed data. It's just amazing. And that leads us perfectly to this final quote from the researchers themselves. Writing this way back in 1999, it's almost prophetic. They said, look, in a few years, technology is going to solve this tracking problem. We're going to have systems that give us perfect player trajectories. The real question, they said, is what can we do with them? And if you think about it, that's the exact question that every sports analytics team in the world is trying to answer today with sensor data. This project wasn't just a series of clever tricks, it was a masterclass in how facing tough limitations can spark incredible ingenuity. They laid the groundwork and asked the right questions. Questions we're still working on almost a quarter century later.